Okay, I want to quickly review some things we talked about the Thursday before spring break. As we're resuming now, we began chapter 4 for those of you that were here, and it's kind of a big step and a big change in a way. We're talking about topic of vector spaces, and this is a little bit abstract in a sense, although there's purpose in why we are doing this. And one of the main things is we'll be able to classify many different excuse me, types of objects, which we will be able to prove things for these in sort of one step because they are all actually vector spaces. And it's really not something new in a way, because the vector spaces we'll be dealing with are things that we're already familiar with for the most part. So let's just get into a quick review. Again, we talked about this if you were here on the day before we went to spring break on that last Thursday. Then this is a review real quick of what we talked about. But simply put, a vector space is a set V of objects that we call vectors. Now, vectors now will be a more general term than the n-tuples that we talked about before. Vectors can be other things like matrices or functions or infinite sequences of numbers. We will still indicate vectors with arrows over them as we write them in the book. They are going to be bold-faced. So it's the set of these objects we call vectors, and then two operations which are defined, addition and scalar multiplication. This is called a vector space. So the vector space is the set of the vectors together with the two defined operations. And it's called a vector space if all the following properties hold. And there's 10 of them. These are sort of the 10 commandments. Each single one of these has to be true. If any one of these is false, then we do not have a vector space. And you can see the axioms, the first three at least deal with the addition operation. The first one is the closure axiom, that these properties are sometimes called axioms. If we add any two vectors in the set, we have to get a vector in the set. If I were to combine or add two vectors and get a vector not in the set, then this would be violated. We have commutative and associative properties of vector addition. We have the additive identity property, which says that the vector space has something called the zero vector, which we denote, of course, that way. A statement such that this statement here is true. The additive inverse property says for any vector u in the vector space V, there exists a vector called the negative of u, which we denote this way, such that if we add these vectors together, we get the zero vector. Properties 6 through 10 deal with the scalar multiplication property. Number 6 is the closure under scalar multiplication. If we scalar multiply any vector in the set, then we must get a vector in the set in order for us to have a vector space. And then we have various distributive and associative properties, and then the scalar multiplication identity property. So, this may be kind of strange. What's all this about? Well, we've actually already looked at this from the standpoint of several vector spaces. We just didn't call them vector spaces. So let me look at some important vector spaces. The ones that you see here in this list, I'm only going to, I went over all of these briefly on Thursday's lecture. If you weren't here, you can read them here, but the ones that have the red dots next to them are really the important ones that we will be using, and you'll notice that these two are very familiar up here. N space, the set of all vectors are n-tuples in n space with the standard operations of vector addition and scalar multiplication as we define them. Those form a vector space. So 2 space is a vector space. 3 space is a vector space. The set of all m by n matrices is a vector space. And the way we denote that, you see the way we denote that. So the set of all 2 by 3 matrices we would designate as M23, for instance. So this is the set of all, this would be the set of all 2x3 matrices. So that set forms a vector space with the standard operations of matrix addition and scalar multiplication. And then I'll just jump all the way down. The next several sets describe sets that contain objects that are functions. Okay, functions, real valued functions, like the function f of x equals x squared, for instance. And so it's a set of functions, kind of a different sort of thing. And this last one down here, what we're going to be using quite a bit, P sub n here, is the set of all polynomial functions of degree n or less with the operations of addition and scalar multiplication. And so those together, well, those with these defined operations for addition and scalar multiplication for functions, though that set forms, again, a vector space. And there are other vector spaces that consist of other objects like infinite sequences of numbers and other such things. But these are the main three that we're going to focus on. Now, one thing real quick we talked about was what are examples that, well, let me first say a trivial vector space is something we call the zero vector space. And it's the vector space containing the single vector, the zero vector itself. Obviously, the zero vector, if we add it to itself, we get the zero vector, so it's closed under addition, that first axiom. And if we scalar multiply the zero vector by any scalar, we get the zero vector, so it's closed under scalar multiplication. So this is a trivial, what we call the trivial vector space, or the zero vector space, but it's a very important one nonetheless. Now here's some examples that are not vector spaces. You might have noticed on the list of important vector spaces that the set of all real numbers, which is really one space, is a vector space. But the set of all integers is not. And the reason is, when we do scalar multiplication, those scalars are real numbers. And so the number 1 is an element of the set of integers. We're using the letter z here to represent the set of integers. But if I multiply, say, 1 by a half, I get a half. 1/2 is not an integer. And since 1/2 is a real number, we are not closed under scalar multiplication, and that was axiom number 6. So axiom number 6 fails, and this is not a vector space. Here's another example. The vector space, or is this set a vector space? And the answer is it's not. Set of all ordered pairs such that the x and y values are greater than or equal to 0. And we can visualize this graphically in the xy plane as being every vector or point in the first quadrant. We also include the origin, 0, 0, and the positive x-axis and the positive y-axis. And most of the axioms actually hold here, but number 6 and number 5 fail because the vector 2, 1 is in this set, right? So if I've got it drawn here, you can either think of the point at 2, 1 or the vector starting from the origin to that point, right? That's the ordered pair 2, 1. It's a vector in the set B. But if I scalar multiply by -1, I get this vector, right? Which would be actually pointing down here, right? And that is not in the set B. And so axiom number 6 again fails, but also axiom number 5. Axiom number 5. And those are the only axioms that fail. By the way, in this example up here for integers, that's the only axiom that fails, actually. So again, just, you got 10 axioms, all 10 have to be true. Here's another one. Basically, this is the x-axis, the set of all ordered pairs x, 0, where x is a real number, and this is the y-axis. And so we're basically looking at the x and y-axis. Okay, this is not a vector space either, because axiom number 1 fails. All the other axioms actually apply and are true. So the vector 0, 2, this one going up here, and the vector 2, 0 are both in the set W. But when I add them together, I get the vector 2, 2, which is shown here. And that vector is not on the x or y axis. And so axiom number 1 fails. Okay, so that's just a quick overview of the idea of vector space. I don't want you to get too hung up in Chapter 4, Section 1. I think there's like 5 or 6 homework problems there where you go through the list of axioms and try and find if one of the 10 axioms fails, and if so, then you do not have a vector space. If all 10 actually hold, then you do have a vector space. What I do want to do is focus our time on Section 2 of Chapter 4, which deals with the concept of a subspace. And so we started that discussion. Let's pull that up here. We started that discussion, and so a non-empty subset of a vector space V that is itself a vector space under addition and scalar multiplication defined for V is called a subspace of V. So if I have a subset of a vector space that is itself a vector space, then we call that a subspace. Now, first of all, what is a subset? What is a subset? Subset A is a subset of B if every vector in A is a vector in B. Okay? Or every object in A is an object in B. So, for instance, a set actually is a subset of itself, because every vector in a set would be in that set. So in a sense, any set is a subset of itself. And so the set itself would be a subspace. Also, every vector space has the zero vector. That was one of the axioms, right? That was one of the axioms, that the zero vector was in the set. Well, if we have the zero vector all by itself, right, that's the zero vector space. So the zero vector space is a subset and a subspace, more importantly, of any vector space. So that's sort of the trivial subspace, if you will. So every vector space has at least 2 subspaces, itself and the zero subspace. What's more interesting, though, is, are there subsets that consist of vectors more than just the zero vector, but not all of the vectors in the vector space itself? Is that subset a subspace? And so, do we have to go through and check all 10 axioms? Well, the thing that happens is, if we have a subset, we automatically inherit several of the properties from the 10 axioms or properties. Number 2, number 3, and 7 through 10 all hold. The remaining axioms, which are 1, 4, 5, and 6, are not necessarily inherited by the subset. However, if we suppose axioms 1 and 6 hold, 1 is the closure under addition, and 6 is the closure under scalar multiplication. If those two hold for a subset W of a vector space, then we have proven here basically that the other 2 remaining axioms also apply. Because if number 6 holds, then and if we have any vector U in the set W, in the subset W, then K times U, right, must be in W, right? It's closed under scalar multiplication. And therefore, if I multiply by 0, right, I get the 0 vector. That must be in W. Well, that's axiom number 4. That says we have to have that 0 vector. Also, if I multiply U by -1, I get negative U, right? That's in W. And since U plus negative U by axiom number 1, which we're assuming holds, that also is in W. So axiom number 5 holds. And so, based on this analysis, here's what we can say. If W is a non-empty subset of a vector space V, then W is a subspace if and only if the 2 axioms of closure under addition and closure under scalar multiplication hold. So that's all we have to check. And that's what we're going to be doing with some examples here in just a minute. I already mentioned this, right? Every vector space has the 0 subspace as a subspace, right? and then we're just describing that here. I want to talk about some familiar vector spaces, 2 space and 3 space, that we're familiar with, and list all the subspaces here, and you can see they're listed here. For 2 space, the only possible subspaces are the 0 subspace, as we said, all of 2 space, and then the only other option are lines through the origin. And we did an example here. This red line through the origin extends forever. If I have any vector, right, this black vector here is on that line. If I scalar multiply it, right, I'm just going to either lengthen that vector in this direction, shrink it, or if I multiply by a negative scalar, it's going to go in this direction. Either way, it's always going to be on that line. If I have 2 vectors, this vector here and this vector here, and I add them together, I'm still going to get a vector that's going to maybe point down this way, but it's going to be on this line. Right? It's closed under addition and closed under scalar multiplication, and that's true for any line passing through the origin. Look at this dashed line here. That's not passing through the origin. Okay. Well, that's not going to be a vector space because, number one, we know the 0 vector, which is the origin, right here, is not on this line. Another way of checking it out is for a point or a vector on the line here. Here's a vector right here. This black vector here is on this dashed line. But if I scalar multiply it by a number bigger than 1, it's going to stretch it out this way, right? And now we're not going to be on the line. So it's not closed under addition. But I do want you to know these facts. And then for 3 space, the only possible subspaces are the 0 subspace, all of 3 space, lines through the origin, and planes through the origin. So just like any line passing through the origin, in 3 space we could have any plane passing through the origin. Now, I do want you to know these facts. Please realize that 2 space is not a subspace of 3 space. Planes through the origin is not 2 space. So please be careful about that. 2 space vectors are ordered pairs. 3 space vectors are ordered triples. Okay? 2 space is not even a subset of 3 space because no 2 space objects are in 3 space. Okay? So I know you get confused when you think of physics. Sometimes you think of the vector x, y in 2 spaces being the same as the vector x, y, 0 in 3 space. But in linear algebra, it is not so because they are totally different objects. So, how do we determine if we have a subspace given a particular subset? Well, here's an example, and we worked through this one in class. And so I have a set W, which is the set of all ordered triples, 1, 0, A, such that A is any real number. Okay, is this a subspace of 3 space? Well, first thing is, what are some vectors in W? Basically, you can choose any value you want for A. For instance, 1, 0, 1 is there, 1, 0, 2, 1, 0, 0, 1, 0, negative 15. Pick any number basically for that last one, and it's in there. Well, the way we're going to show whether or not we have a subspace or not is showing that if it's not a subspace, let me say that, we're going to give an example that shows it's not a subspace, a specific example. And that's what we've basically done here. So the vectors 1, 0, 1 and 1, 0, 2 are both in the set W, right? But if I add them together, what do I get? By vector addition, I get 2, 0, 3. 2, 0, 3 is not in the set. Why? Because the first coordinate here, the first component of this vector to be in W has to be a 1. Right? So we're not closed under addition. And W, therefore, is not a subspace. Make sure you indeed answer the question, right? Make sure you state whether or not W is a subspace. In this case, it's not. It also turns out that W is not closed under scalar multiplication, because if I multiply any one of these vectors by anything other than 1, I'm going to end up with a vector not in the set W. So this is really not a subspace, obviously. Some of you might have noticed it's not a subspace because the 0 vector, right? 0, 0, 0 can't be in this set. Okay, but again, the way we're going to, even if the 0 vector is in the set, that doesn't guarantee that we will have a subspace. Okay, so in the next video I'm going to show an example that is a subspace, and in that case we're going to have to prove it using the theorem we just cited a minute ago. That is, to show we have a subspace, we simply show closure under addition and scalar multiplication.